All right, so I'm going to talk a bit about a range of things, and this will serve as an introduction for the Threshold Summit overall. I'll talk a bit about threshold cryptography in general. I'll talk about drand and the motivation for the protocol. I'll talk about the League of Entropy and the successes there. Then I'll talk about kind of what's coming next for drand and these kinds of networks generally. So I first want to start by motivating why Web3 is a great place to build these kinds of protocols, why Web3 can enable secure global digital utilities, and why we should be leaning into the tooling of Web3 to build pretty robust infrastructure. So Web3 is an evolution of the web, which itself is an evolution of the internet, to add verifiability and trust to transactions online. Web 1 and Web 2 relied way too much on specific server infrastructure to remain honest and continue fulfilling the things they say they will do. And because we have cryptography, we can make the transactions themselves verifiable, and we can use that verifiability to build applications like financial transactions or encryption schemes or all kinds of verifiable interactions between participants. Or we can additionally create verifiable infrastructure. So you can create infrastructure that agrees to behave in a certain set of ways, and you can check that that's happening and either reward participants for doing so or punish them if they don't behave according to the protocol, which gives you the ability to create a better infrastructure. So from my perspective, Web3 can give you a way of encoding digital human rights into the infrastructure layer by establishing cloud infrastructure that respects the guarantees provided to the users. So you can think of encoding various different kinds of rights and so on in specific kinds of systems. And when we think about some of the stuff that we're going to talk about today, randomness, basic encryption schemes, signing messages, encrypting messages, all of this kind of stuff, these are fundamental building blocks to be able to enable these kinds of systems, which then themselves can give us these kinds of rights. So this is important stuff. And so you can think of, on the whole, as the whole Web3 goal set to replace the underlying layers of the internet with math, cryptography, and economics. If you can build self-sustaining networks out of these rules, out of these verifiable rules, then you can end up with a much more secure set of applications and therefore superpowers. You can think of Web3 and the blockchain infrastructure model as a way of giving you a public international digital utility that can serve anybody around the internet and give you the ability to use the network without having to request permission or being subject to specific policy constraints that might drop you off the internet. And so I argue that that's a much better foundation on which to build internet infrastructure. So let's talk about threshold networks for a moment, and I'll just give a very high-level introduction. Other people will likely dive deeper into this. But the basic idea of a threshold encryption scheme is that you have a secret of some sort that you then encrypt or transform into a set of shares of that secret, and you give those shares of a secret to a range of parties, which will become the participants in the threshold group or the threshold network. Then you can use a subset of those parties to sign a particular piece of information, and that signature is valid. This is a very fundamental building block that can show up in lots of other kinds of protocols. You can use this to verify that certain transactions are correct. You can use this to sign things like time. We'll talk about that in a moment. You can use this to sign things like randomness. You can also use these encryption schemes to decrypt messages. So you can encrypt something to the threshold set, and it requires a certain K fraction of participants to decrypt that particular transaction. So you can see how this could be plugged into blockchains as well, where you can imagine encrypting transactions ahead of time, publishing them to the network encrypted, and then decrypt them after the fact once they've been linearized. So this would be a way of getting rid of a lot of MEV problems and so on. So the applications are extremely broad already in the crypto space. In the cryptocurrency or blockchain space. You can imagine how this has wider applications than just broad internet infrastructure. And the general way that these networks tend to look is something like this. There's some initial protocol or ceremony to generate the private key. you take that private key and you give separate shards to the network. This particular step can be done in many ways. Some parties have some kind of complicated MPC ceremony between one set of participants and then give the key to a different set of participants. Or you can take just one. Nowadays, we tend to have really good protocols that enable that initial set of participants to generate the key themselves and then initialize the network with a particular protocol. Then you go from, now that you have this threshold network of parties, you can use it to sign messages or encrypt or decrypt messages and so on. Now, the fundamental trust assumption in threshold cryptography and threshold networks in general is that you will not have collusion up to some fraction f of attackers. And so as long as f plus 1 participants sign a message, you know that it's, am I saying that right? I'm probably not saying that right. You require a fraction f to remain honest. And as long as f plus 1 signed the message, or as long as f signed the message, you're good. Meaning you have some threshold of honesty or correct behavior. Now, of course, in game theory terms, relying on honest or altruistic participation is risky. You don't have like as strong of a guarantee in a very rational world that parties won't be corrupted over time, won't be biased economically, and all kinds of things. But in general, these networks have stood the test of time and have built very large-scale systems that behave correctly. And so initially when we first started building drand and so on, there was a big question as to how well accepted this notion was going to be, whether people will be in the kind of honest, malicious model, or they would want to be in the Byzantine, in the rational model where you have to guarantee certain economic outcomes. And then we took kind of like one of the first steps to go in this honest model. So many other participants since have built a lot of networks in this kind of structure. In fact, even today, a lot of the proof of stake protocols rely on honesty assumptions in the stake guarantees. So they expect that a certain number of participants will remain honest. I think in the long term, we have to build stronger systems that truly are correct in the rational case. But those kinds of systems are much harder to build, and we need larger scale economic networks that are much harder to attack. So today, leaning on reputation and leaning on honesty is the way that a lot of these networks have to go. One of the neat things, and I think this may be open problems, not necessarily open problem in a research sense, but open problem in terms of implementation. I think binding these kind of honest types of schemes with long-term reputation protocols with staking could be a way of getting the best of both worlds, where you could have a set of protocols that require honesty but give you a way to demonstrate bad behavior. And as long as you have that, you can take a separate reputation system and then punish participants, use staking to punish participants. So you could imagine that we could build a large-scale network of threshold networks in a sense that all rely on the honesty assumption. But then separately, you could have a place where participants stake vast sums of money, and they agree to participate correctly in all of these networks, and anyone can present any artifact that they've behaved incorrectly to slash them in that network. So systems like that could be built. Cool. So that's kind of broadly what I was going to say in threshold networks. And again, they have wide-ranging applications and in all kinds of protocols today, including ZK and FHE. In FHE, they tend to be used for encrypting, decrypting the FHE ciphertexts. Great, let's talk about drand. So drand started as a foundational protocol for randomness, and this is what brought us and got us really excited about drand in the first place. You can think of the internet as being composed of a range of foundational protocols, things like the IP protocol itself, things like BGP, which give us routing, DNS, which gives us naming, all kinds of things that the IETF over the last few decades has been building. And NTP is one of those protocols. NTP stands for the Network Time Protocol. And it was built about 35, 40 years ago when the internet needed a way to tell the time correctly. People built a foundational internet protocol that was very simple. It did one thing and one thing only. It did it very well, which was to synchronize a set of distributed clocks around the world, providing a publicly available network-wide clock that everybody could rely on. The architecture was basically built like this, where you had this set of tiers where at the very root of the tree, you had a set of atomic clocks. There's usually cesium clocks of some sort. A set of servers are connected to those clocks and are able to synchronize time between each other and arrive at as close as you possibly can notion of what time is on Earth. You establish the notion of network time. Even this is like you start hitting like Einstein relativity sort of stuff here. You really care about the latencies in between and so on, and you establish the notion of like, a sphere of time around the Earth that we all roughly agree is Earth time, even though, from our relativistic frames, you can't actually get simultaneity. But anyway, that's good enough for we don't have to like do something in the nanoseconds here. We are trying to get clock synchronization in the millisecond scale, and so that this is good enough for us. Then on top of that tier, because we don't want the entire internet to DOS this tier, we build underlying tiers that spread out and relay that time. Now, of course, each tier introduces a little bit of drift, and so you need very low latency here between these parties, potentially regional relays that can give you really good clocks. So this was a design in 1985-ish, and to this day, most of the time around the planet gets set thanks to this protocol. This protocol is running so much of how the world works today. If this protocol went away, overnight, this would be like chaos and catastrophes all over the world because all kinds of important infrastructure relies on this. I kind of know that because random anecdote, some of my code almost accidentally, somebody used some of the code that I wrote to almost accidentally take down NTP, but story for another time. Anyway, in the last 5 years, now we needed a way to get randomness. In the same way that we need to get time across the world, we need a way to get unbiased randomness that is verifiable. And so the internet needs, again, a foundational protocol of the NTP sort to create a verifiable, unpredictable, unbiased randomness source that is publicly available to anybody in the world. And so we, inspired by NTP, a set of folks built drand, which is a networking protocol for distributed randomness. It functions as a randomness beacon, generating notions of randomness along the way, and doing this over any kind of packet-switched network. So this means IP and everything in the modern internet. But you can imagine all kinds of networks being able to lean on this, including giving secure time in space. You can imagine other drand networks somewhere in space and whatnot. And it follows the same rough architecture as NTP, where you have a set of drand nodes. These are the ones that these use threshold cryptography to establish a key and generate a random beacon together by agreeing to respect time. This is where the honesty assumption comes in. The participants agree to respect the clock. They themselves get the clock through NTP. And then you bootstrap randomness on top of time, and you can now create a randomness beacon that emits some randomness over time. And you need a sort of layer of drand relays that are protecting the drand nodes from any kind of DOS situation, and then bring the randomness to all kinds of networks, and then the clients can then get the randomness from them. There is kind of like a trust assumption here that the relays are not going to front run you or something like that, and like do something with the randomness and whatnot. But this is a very solvable problem where you could encrypt the output, flush it out, and then decrypt it as a second step. But that's a whole other sort of network. I think that this works really well for most use cases. Anyway, so drand, we believe, can become a foundational internet protocol for randomness, in great part because of the simplicity of the design and the wide range of applications that can be built on top of it. And so this is what initially attracted us to drand as a protocol when we needed to solve a problem in Filecoin. So return to this. I'll describe kind of like the problem in blockchain networks in a moment. So blockchain networks today need a notion of distributed randomness that is secure for many reasons. One of those reasons is consensus. We need to be able to extract some verifiable, unbiased randomness through a process, sort of shared process, to pick blocks in a proof-of-stake protocol. So randomness is a key feature in these modern proof-of-stake protocols. And in the 2017, 2019 era of proof-of-stake protocol build-out, how to get the randomness was a huge part of a ton of protocols like Algorand and Snow White and so on. An enormous amount of the complexity in those protocols and complexity of implementation came from trying to build a shared notion of randomness. And so being able to decouple the job of generating the randomness separate from the consensus protocol gives you a dramatic design. And so this is where Filecoin needed and used this structure where we rely on the drand network emitting a random beacon over a period of time to then extract the randomness that we need to then select parties to win in consensus. So that's one of the main foundational applications of randomness. But you can also imagine how there's all kinds of other applications in cryptocurrency networks that need randomness. Everything from the encryption, decryption of, that's time. Let me get. You can think of things like fair lotteries or games or games of chance or actual computer games. There's all notions of needs for randomness in financial transactions, in modern applications of all sorts and whatnot. You even need randomness in all kinds of simulation applications where you would like to be able to get a verifiable notion of randomness to know that the seed to some important simulation that you're going to use wasn't biased in some way. So again, the applications are pretty broad. And the neat thing about this kind of thing is that the world hadn't built already some randomness protocol in the IETF days for a bunch of reasons. But it turns out that blockchains can serve as a great development group to build up this randomness protocol and enable the whole internet to benefit from it. So yeah, and so Filecoin, these days, today, it's a large-scale, massive-scale crypto-powered storage network. It relies on drand for its consensus layer, and it relies on drand for other components. And it's been working super well. Like when we first introduced this model in 2020, it's a big question as to how well this would stand the test of time. And we're 4 years in, and it all works super well. So kudos to everybody involved in building this. And so the way that we ran and built that network was that we initially formed the League of Entropy. drand is a project that started at EPFL, and a set of researchers there invented and designed the protocol and built the first implementation. Then Cloudflare got super interested in this protocol and started deploying it themselves. We also got interested in the protocol around the same time, and so we joined what we described as the League of Entropy initially. And so we brought together 5 organizations, EPFL, Cloudflare, Protocol Labs, the University of Chile, and Kudelski Security, to bring together the 5 initial members of the League of Entropy that together would compute the randomness for the internet. Now, 5 parties is really it's maybe secure enough given the reputation of these organizations for some kinds of applications. But if you want to secure billions to hundreds of billions of dollars, and you want to prevent attackers from attacking these organizations, you need to increase the scale of your network. And so today, the League of Entropy now has way more partners, and it has an entire process for applying to join the League of Entropy, getting the software and participating, and so on. And it's been really, really exciting to see a ton of partners over the years join the League and help support these kinds of networks. And since then, the League of Entropy drand network is now used in all kinds of applications across the blockchain space. So we've seen not just the consensus use cases that I mentioned, but it's starting to get used in many other sorts of networks. I think other folks can talk more about that. One of the other things you can build on top of drand is time lock encryption. It's one of the things that I'm pretty excited about in general. And I think this is one of those primitives that is just so awesome and powerful that it can really be used for a lot. And this is one of those areas that can be productized in a bunch of different ways. And I think we just haven't seen yet what these kinds of primitives can do. The idea of time lock encryption here is that you can use the threshold encryption scheme, the same model of drand. You can even use the same exact network to create the ability to encrypt data into the future. So that means you can take a message, encrypt it to some future point in time, and once the time arrives, then the threshold network decrypts. The threshold network gives you the key to be able to decrypt the message. And so you can do this. Imagine being able to take troves of documents that you want to encrypt to the future, encrypt them with this key, and then store the ciphertext on IPFS or Filecoin or something like that. And nobody can read the contents of the documents until a given moment in time. At that point in time, anybody can decrypt the messages now. You can also, some parties don't want the decryption to be public. Some parties want still some notion of access control. Now that just means introducing another layer of key management where what you encrypt initially is a decryption key of some sort, and you might have like some scheme where you both need to hold a capability in the form of some key plus the other decryption key that will be revealed in the future. You can use those two keys together to then decrypt some artifact. So this is a way where you can productize really critical types of use cases for all kinds of compliance type use cases where documents need to be stored for long periods of time, or documents need to be classified but decrypted at a certain point in time. You could do this to all kinds of government documents, right? So that many governments around the world have concrete classification and declassification time periods where certain things need to remain secret for some period of time, but then verifiably be published at a certain point in time. And so these kinds of time-lock encryption schemes let you do that in a public and verifiable way internationally, where you can properly commit to decrypt a certain set of information. You can even generate proofs that the information is correct and is the information that you're intending to store. So everyone can know verifiably what's stored in that encrypted ciphertext. The time passes, and at some point, now everybody can decrypt, or the select set of parties can decrypt and look at the information. This also is the same. I mentioned earlier the way of encrypting transactions. My claim is that blockchains in general should move wholesale to this scheme, where participants that use blockchains should submit a time-lock encrypted transaction into a blockchain so that you can linearize ciphertexts with no ability of parties to do any sort of censorship or MEV, minor extractive value, any kind of MEV hacks, to be able to properly get your transaction in, and then after that happens, then decrypt it for everybody and execute it. And so I think that that's a better model for crypto networks. And I think if time-lock encryption was available in 2014, then Ethereum would have been built on this, and so many other networks would have been built on this, and we would have a dramatically better time of things today. Cool. So then, and again, there's lots of different kinds of applications that you can build on threshold networks generally, on randomness, on time-lock encryption, and whatnot. You'll hear more from other folks. Just some quick thoughts on over time on kind of like the next stage of development since last year. Again, in the history of drand, started as a research project at the EPFL, then Cloudflare and PL and other folks got involved in developing the protocol. Then when Filecoin needed to use it, we productized the whole thing and enabled a much larger League of Entropy to operate. We helped build up a larger group. And now, given a range of the possible applications, we think what we need or we thought last year what we needed is an organization that could help productize a lot of these particular use cases, work with end users and consumers of this, like other development teams, to be able to implement these kinds of applications, to be able to get the benefits of drand and other threshold networks. And so we decided to build a company for that, which is Randomoo. So this was part of PLVS. PLVS is the Protocol Labs Venture Studio. We posted this last year in terms of being able to productize drand. And now it's super exciting to see that Randomoo is a company and it's a group. And you'll hear more from them in a bit. And so I think this is pretty exciting for drand in general and for threshold networks in general. There's, again, a ton of applications that are possible. And the Randomoo team is the team that has been operating and running a lot of the League of Entropy and helping steer the project. I'll maybe conclude with some quick thoughts on public goods funding. So this general scheme of weaving crypto networks together is not just unique to us. Many other participants are trying to do this. If you were to plot like an actual diagram of all of the interactions and interdependencies across crypto network, you would get this like time entangled thing with lots of networks depending on other networks. And so there's a dependency graph not just in software, but there's a dependency graph on running systems. And what we really need is some structure by which the networks that depend on other networks are able to flow value to those networks to build up the dependency, to enable the development of those networks. So The way I tend to think about this is think of structures where capital flows of networks can be modeled in terms of individual units of value flow. These could be ideally, completely on-chain mechanisms. This diagram is just coming from the Filecoin network, but you can think of Gitcoin and Optimism Router PGF and all kinds of other protocols as being similar, where you have specific organizations or on-chain mechanisms distributing public goods funding. And so what I want to kind of like see in the world is where one crypto network that depends on another network of some sort flow resources directly on the protocol to the dependencies, right? And when we need some way of adjusting these measures on-chain over time as new dependencies come up and new protocols get used, that the amount of rewards flowing to those protocols and those networks should change. As dependencies stop being used, you need to be able to reclaim those resources. So we need some way of adjusting the value and capital flow of these networks directly on chain. Now, in between now and then, we can do a lot of this through the standard governance protocols across all of these networks. This means Ethereum improvement proposal type things, Filecoin improvement proposal type things. It also means DAO proposal voting and so on. So there's a lot of DAOs out there with fairly large sets of resources that govern and control certain protocols. They should be funding the public goods that they rely on, and we need better ways and structures to do this. One of the really cool things that happened already was that some of the users of drand already are doing this, where they individually said, hey, we use drand, we would like to flow value to drand because we are, in a sense, a customer of drand, and they flowed tokens to the drand network already. Cool. So that's all I have. I can take maybe one or two questions, and then I'll stop there.
Any questions for Juan? Come on. One question. There we go.
Hello, my name is Tony from Space Shard. Amazing presentation, thank you. My question is regarding D-Lock. You said it could mitigate like malware attacks and like, but how it's combined with the transaction that you need to switch state from state A to state B? How do you know what need to be done? I mean, what's the technical? I mean, it sounds interesting, but I don't.
I'm gonna die here one of these days.
Thank you. And maybe in the future, what I can do is, or what people can do is say the question, then the speaker can repeat it, and that way you can get it recorded. So I'll give you like a quick version of the scheme, and what I'm about to say might be incorrect, but this is like hand wavy the way that it should sort of happen. What you can build on the chain is you want to decouple the process of linearizing transactions from the process of executing transactions. And so what you could, I guess it's like generating the transaction, which happens already off-chain, submitting the transaction, which is an interaction between the party generating the transaction and the blockchain, then linearizing, which is arriving at consensus on the order of transactions, then decryption, and then execution. And so you can submit the ciphertext and linearize it into the chain, and then run a decryption scheme on top of that linearization to then be able to execute. And so the state tree that you care about is the final one once the transactions have been executed. But because you've linearized them correctly, a set of them will get decrypted and then executed. So today, some blockchains work in the way that when you submit the transaction, the process of adding it to the blockchain changes the state tree. Not all blockchains work that way. Filecoin, for example, already has baked in the ability to submit transactions and then execute them. So today, in the Filecoin blockchain, you make a transaction, you submit it to Filecoin, Filecoin adds it to the blockchain, it linearizes it, and then it executes it in the next block and changes the state tree in the next block. So you can imagine adding just a decryption layer right there, and so you could go from the current on the clear transactions in Filecoin to time-locked encryptions in transactions in Filecoin, probably just using the same scheme that we have today. You might need to introduce one additional block of latency, but I don't think so. You might be able to just do it right as it is. but I would have to look at the specifics more of how the T-lock structure works today. But yeah, hopefully that answered the question. Any more questions? Cool, awesome. Thank you very much.